Alright students, welcome to Chapter 4 of Health Science 349. So up to this point, we've talked about different measures of central tendency, as well as measures of dispersion or variability, and being able to describe our sample using these statistics. What Chapter 4 is all about looking at tables, graphs, to be able to get the same point across. Instead of using statistics, we're using images. So let's take a look at Chapter 4. So the objectives are to know when we can use the appropriate graphs given the level of measurement. Hopefully from last week you've started to get the idea that level of measurement is really important in determining whether or not we use the mean, median, or mode, whether or not we can use the range, standard deviation, interquartile range. And now we're going to learn about when can we use pie charts, bar charts, histograms, line graphs, box and whisker plots, depending upon the data that we have. We'll also learn how to construct and interpret a box and whisker plot, and also introduce these new terms of modality, skewness, and kurtosis. Notice that in this chapter, I'm not having you guys learn any new calculations. However, in the textbook, they do cover calculations for skewness and kurtosis. We will not be going over this, so you do not have to know or read that section. Alright, so as I mentioned, graphs really depend upon the level of measurement that we have for a variable. So when we have nominal variables, really we can only use pie charts and bar charts. Same thing with grouped, ordinal, interval, and ratio variables. We can use a pie chart and a bar chart. And really, if you think about this, what are we seeing in a bar chart and a pie chart? These are describing different categories or different groups of people. Right? So really, when you're thinking about this, these categories, these graphs, are just describing groups of people, not necessarily numbers or data per se. However, when we're talking about ungrouped interval ratio variables, so we're talking about what is your age, and you just give me a number. Or how long did it take for you to run a mile? You gave me a number. As opposed to if I said, what's your age? 18 to 21, 22 to 25, that would be an example of grouped interval ratio as opposed to ungrouped interval ratio. And so with ungrouped interval ratio variables, we can do pie charts and bar charts just like if we had a nominal or grouped variable, but we can also create histograms and also line charts. There are other graphs that your textbook mentions at the beginning of the chapter, such as frequency polygons, frequency distributions, and cumulative distributions. Don't worry about those. Know about them and know that they exist, but we're not going to be tested, nor do you have to create or know how to interpret those types of graphs. Okay, so one thing that's going to be present in all types of graphs that we create and that we'll see are the answers to what the variables are. So if we look here at this graph here, this bar chart, we see this is displaying our favorite sport. So on the x-axis or on the y-axis, which one are we going to find the answers to this variable of favorite sport? Well, we're going to find it on the x-axis, right? We see that it shows sports, and we see that it's soccer, softball, basketball, and other are the possible responses for this. So on bar charts and histograms, we're going to see that the x-axis is going to display what the possible answers are for variables. So that leaves the y-axis to describe and tell us what the frequency is for each of these answers. So you could say how many people said that basketball was their favorite sport. Well, we see basketball going to the line here corresponds to a number of 6. So we see that 6 students said that basketball was their favorite sport. Pie charts. So with pie charts, we can use these for pretty much all levels of measurement: nominal, grouped ordinal interval ratio, and ungrouped interval ratio variables. And really what we're looking at in a pie chart is just really the size of the slice, right? The biggest slice is going to be the mode, which has the biggest frequency. That's the most people that make up that sample. But one thing that we don't see, and we can't figure out from a pie chart, is the median. Even more so, looking at this variable here, community. would it make sense for us to calculate a median or a mean for this variable? It wouldn't, right? How would you make sense of a mean community or a median community? It doesn't make sense. What's the most common community that people identify with? That makes sense. The mode. So if we're looking here, which one has the biggest slice? Samoan. So then, which one's the mode? Samoan. Alright, so now let's look at bar charts. So bar charts, just like pie charts, can be used for pretty much all levels of measurement. For nominal, grouped ordinal, interval ratio, and ungrouped interval ratio variables. Now notice that in these bar charts, there are gaps in between each bar and in between each category. And the reason for this is that each of these bars represents a distinct group of people. So if we're looking at the left chart, favorite subject, we see that the most people that said that music was their favorite one, that is just music. Language, art, science, reading, those are all different groups of people that said that that was their favorite subject. Just looking at amount of pressure, none, very little, some at all. Again, these are distinct groups of people, categories, which is why we see the gaps. And, like we've seen previously, the tallest bar is going to be the mode. One simple way of identifying a central tendency measure. However, similar to pie charts, are we able to see where the median and where the mean are? We're not. So that's another limitation of bar charts, similar to pie charts. All we can get out of here is the mode, the one central tendency measure. So histograms. We use histograms for ungrouped interval ratio variables. So again, ungrouped would be giving me just a number. Compared to grouped is where we have ages 0 to 5, 6 to 10, 11 to 15. Each answer falls within a group. So just like a bar chart, but a histogram looks like this. And notice that there are no gaps between the bars. And the reason for this is that people can fall in between these bars. Right? The gaps before indicated that each bar was a separate, distinct group. In this case, because all the bars are all pushed together and there's no space in between them, if we see here we have ages in the intervals of 10. Well, it is possible that somebody could be 10 and a half years old, somebody could be 42 years old, even though the histogram only shows us 10, 20, 30, 40, it doesn't mean that somebody could not fall within those units or fall in between the bars themselves. So we use histograms when our ungrouped interval ratio variables are continuous, not discrete. Notice that also at the bottom, they're actually numbers. We don't see math, we don't see literature, we don't see science, we don't see none, we don't see all, we don't see tomorrow, right? These are all just numbers. This is a key feature of histograms. It all deals with numbers. Just like a bar chart, we know that the tallest bar in a histogram is indicating the mode. But what if I ask you age, but as a grouped interval ratio variable, such as we see here? Well, if we did this, and we were still to run a histogram, all that SPSS is going to know is not that individual's age. It's going to know either 1, 2, 3, or 4 based upon the person's age. When we use grouped interval ratio variables, and we're saying, well, yeah, it's an interval ratio variable, I could create a histogram. Wait a second, because we're using grouped data. So when SPSS sees this 1, 2, 3, and 4, it's going to think that it's age 1, 2, 3, and 4. So here we go. Here's a histogram. What is your age? 1, 2, 3, and 4. Frequency, how many people? So you see about almost 100 people said that their age was 1. Does that make sense? That doesn't make sense, right? And even more so, take a look. Every histogram you create in SPSS will give you 3 pieces of descriptive statistics. It will give you the mean, the standard deviation, and your total sample size. But knowing our age variable, does this mean age of 2.69 make sense? Knowing that we had a group of children and adults? It doesn't, right? So this is why whenever you have grouped data, grouped interval or grouped ratio variables, you do not treat it as ungrouped. You don't treat the codes for the groups themselves as numerical data, as real numbers. Okay, so then how do we actually display data for grouped interval ratio variables then if we don't use a histogram? Well, we can create a bar chart or a pie chart. Right, remember that we know that the 4 different groups all had a certain age group or age range. And so this is one way that we can display the data. Now we can see how many people were 21 to 29 years old, either in the blue pie slice or in the first bar chart. And notice now that we create a bar chart, there are spaces in between the bars themselves, unlike the histogram. And we see that the age themselves is the actual category, the age groups, not the actual code themselves of 1, 2, 3, and 4. So all this talk about grouped interval ratio variables. So there are certain rules that have to be followed when creating categories and creating groups. First one is jointly exhaustive, is that you have to consider every single possible score. And every single possible score has to fall within a category. The other one is mutually exclusive, is that one person's score can only belong to one category, not multiple categories. And lastly, equal in size. Each category should include the same amount of numbers within each group. So in here we have ages from 0 to 5, age from 6 to 11, ages 12 to 17. Notice that each of these 3 groups have 6 whole numbers in each of them. Each category is equal in size. So let's see how all 3 of these are actually played out in an actual table or in a graph. So here we see age and the number of deaths as far as it's measured by case fatality ratio. But really don't worry too much about the bars themselves or the y-axis so much, but look at the x-axis. Look at our age groups. Notice that no matter what possible age somebody can say they are, they're going to fall within one of these groups. They have somewhere to fall into. So jointly exhaustive. If somebody is 20 years old, they're going to fall within right here. If somebody is 85, they're going to fall in here. If somebody is 2 years old, they're going to fall here. So no matter what people say as their answer, they have somewhere to choose. They have a category to fall under. Mutually exclusive means that they're only going to be able to choose one and only one category. So here we see 18 to 19-year-olds, 20 to 29-year-olds. Well, what if this changed and I created 10 to 19 and then 21 to 29? Then what happens? What if you have a 20-year-old? Where are they going to go? That's jointly exhaustive. That addresses the jointly exhaustive rule. But what if I said 10 to 19, 19 to 29, 29 to 39? Well, now in this case, someone who's 19, well, now they can choose. Do I want to go in this category or go in this category? Or from 29, do I want to choose this category or this category? We don't want that. We don't want to give that many choices, because then now, if that is the case, then we're saying we have multiple people in our sample, but really those multiple people are really just one person, but they double dipped essentially. And then we see that each of these age groups, 0 to 9, 10 to 19, 20 to 29, are all in the increments of 10 years, with the exception of the last increment. Sometimes you will see greater than 70, sometimes you'll see less than 9. And in this case, as long as the end intervals, the end groups, either the very low or the first one or the very end or the last one, as long as the ones in the middle are all equal in size, then you've met that rule. Okay, the line graph. So take a moment to look at these two different graphs. The first one on the left is telling us between the years of 2004 to 2010 the number of deaths per 100,000 in the population for antidepressants, benzodiazepines, cocaine, heroin, and opiates. The second graph is showing us the same time point for the same drugs, but now it's showing us the number of emergency department visits. Take a few moments, pause the video, and see if you can come up with a little story, with a little bit of some result or some conclusions that you can draw from looking at both of these line graphs. Okay, so hopefully you were able to come up with some conclusions and draw some results from looking at these line graphs. So looking at the first one, deaths per 100,000 population for these 5 drugs. What we see, most people are dying from opiates compared to all the other drugs. And also we see that there's been a drop in cocaine deaths starting around 2006, and it's kind of evened out within the last year, 2009 to 2010. So if you were a drug czar and trying to develop drug treatment programs, in this case, you see that you definitely want to focus your efforts on opioids, and maybe not necessarily on cocaine or even heroin, because even then we see for heroin, it's the lowest number of deaths that we see occurring compared to all the other drugs. What about emergency department visits? Well, we see there's been a big spike, a continuous spike, of people going to the emergency department for opiates and also for benzodiazepines. Right? And the same thing, we see the same thing is holding true with cocaine, that around the same period that there was a drop. And then we see a little bit of increase of people going to the hospital. And again, we see that increase from 2009 to 2010, people going to the hospital, but not necessarily dying so much. Right? So some of the stuff that we can get from looking at a line graph is really looking at trends and looking at things over time. So from 2004 to 2010, we can see that there's been a steady increase in almost all of these drugs in the number of emergency department visits and number of deaths. That's pretty startling information here. And again, it helps you drive policy, helps drive prevention and treatment programs.